In the Workbench, help and information is offered where and when you need it. Let's take a look at the execution environment shown here. A user may browse over elements of the editor to learn about them. For instance, the plugin repository element is highlighted in red, and the message informs the user that configuration of this element should be done first. More information is attached to the not loaded element and indicate how to install a copy of the plugin repository on the analysis machine. Help is context dependent. For instance, let's press return to create a download area here. Browsing over the highlighted elements provide a help message that explains what the area is for and how to create new locations within it. Let's press return. We have now created an element inside the download area, and the highlighted element now provides help to explain what the directory is for. Now that we understand this, we can locate the download area and bind it in this location. You can see that the messages that were shown before are no longer available, but if we deleted this area, now the message is back, so that they only show when they are useful to the user. This capability alleviates the need for detailed offline documentation. In the Workbench, nodes are used to represent parts of the computational infrastructure, software systems, or data used or produced during analysis. As an example, let's create a node to represent an execution server. To do this, you right-click on the model name in the Project tab, select New, and locate Execution Node in the cluster config language. The execution node concept represents a server in the Workbench. Finally, you invoke the menu item Execution Node to create a node of this concept. An execution node has a name and a server address. Let's configure this node to represent the lab web server. We set the server element to compineLab.org and enter lab web server as a name. The name is used to locate the node when a reference to the server is needed in other nodes configured in the Workbench. The server address is used when connections are needed to be made to the node. This introduction video uses execution node to showcase the capabilities of the Workbench, because you are likely to be already familiar with a computational server as it is modeled here. Whether we use nodes in the Workbench to represent many aspects of data analysis. For instance, we use nodes to represent, track, and act upon sets of files under analysis. Nodes can be manipulated with operations. Most operations are context dependent. Let's illustrate it with this execution node. One operation available on a node is to test whether the node is reachable with ping. Running this operation indicates that the node is not reachable with ping. Since the node is a web server, however, we can define port 80 and test if the node is reachable on this public port. To define the port, press return here, enter 80. To test if the node is reachable, if the port is reachable, use this intention. You see that the status has been updated to reachable. Now let's test if port 22, which is the SSH port, is reachable. So we can do the same thing here, and after a suitable time, when the timeout expires, we have determined that port 22 is not open on this server. The interface of the Workbench is highly interactive. To illustrate this, we define an ad hoc cluster. An ad hoc cluster is simply a collection of servers that you can use to run computation. We named this cluster. The cluster has a number of cores, which is calculated dynamically, as you'll see in a minute, and has a collection of nodes. At the moment, there's no node attached defined in this cluster. We can press return and add a node. We can add the lab web server, a reference to the lab web server that we have just created in the model. You see that there's no core defined. So let's find out. We can navigate to the server, and we see that indeed we did not define the number of cores. So now we can go back, and we see that the total number of cores has been updated. We could add the lab web server twice, but that doesn't make much sense. Instead, we can create another execution node, and we'll call this node 1. We'll put 16 cores on this, and let's go back here and add it. Node 1 is available. Okay, that's good. Let's demonstrate copy and paste. We can simply create several copies of this first node. We will change the name here, leaving the number of cores to 16. And let's say this one has 24 cores. We go back to the cluster, and now we can simply add references to the 3 cores, 3 nodes. So let's say you don't want to use the lab web server for computation. You simply inactivate this server, and you don't remove it because perhaps in the future you would like to run some computation on this node. You see that the number of cores is automatically updated. So this shows that we can very easily copy and paste information nodes with their configuration. We can reconfigure the pasted node. We can create references to nodes with autocompletion that points to their name. We can navigate to the nodes using those references. Something I haven't showed you is that there's full undo redo support in the Workbench. So for instance, we had inactivated the lab web server. The last thing we did before that was to add node 3. So we can actually undo those changes with the Workbench. In addition, we can redo those actions. And all of this is recorded transparently by the MPS Workbench that's used as a platform for the NYoSh Workbench. Of course, there is a lot more to the NYoSh Analysis Workbench than can be covered in just a few minutes. For instance, the Workbench can run all the Gobi Web Analysis plugins interactively. Let's have a brief look at a few of the plugins already provided in the platform. Here's a list. We can use a query functionality here to narrow down and look for keywords. So for instance, you see that we support a number of plugins that take advantage of BWA. We also find bowtie resources and plugins. We can find, for instance, Bismarck is represented here, and so on and so on. The plugin system comes with differential expression analysis, with DSeq, with EdgeR, with Gobi, and so on. A complete description of the Gobi Web plugin system is available in our prior publication, listed here. Nice interactive views of large tables of data are also supported. Let's have a look. This example illustrates how a custom user interface here can be embedded in the Workbench and combined with custom languages. The table is interactive. You see that if I change the query term here, the component is refreshed. We use the Lucene query language to retrieve rows and columns of very large tables of data produced by Gobi Web plugins. This example concludes this brief introduction. You may find more information at workbench.combinelab.org.